Hello. In this video, I would like to introduce Fuzz Introspector, which is a recently released tool, and I think it was just made available open source 2 months ago or so. And the purpose of the tool is to provide insights about the fuzzing of a given project, and in particular to provide some type of guidance on how to improve fuzzing of a given project. Now, one of the key ideas behind this tool is to use some static analysis techniques and then use the output of those static analyses to give some insights about the fuzzing of a given project, such as understand what are some interesting targets in a given project, understand how well the existing fuzzing harness performs a given project, or even to match the coverage of the existing fuzz drivers with their respective reachability of these fuzz drivers. And the tool is developed under this open source security foundation, which you can see here. And it was introduced here by Google early 2022. And Adalogics has also been has been a key player in bringing this project to life. Now, in this video, I would like to show the tool by going through this integration it has with OSS fuzz projects. So it has essentially been developed in a way that makes it possible to run on a large number of the existing projects that are integrated into OSS fuzz. And in order to do this, I will simply just follow the instructions that are on the GitHub of Fuzz Introspector. So if we go into the OSS fuzz integration, and you can also see, so first and foremost on the README, you can see that it has a long list of features, and it also then has instruction on how to test this with OSS fuzz, and that's exactly what we're going to follow. So the first thing we're going to do is we're just going to clone the repository over here, and it's going to go fairly fast. And then the only thing we have to do is we have to run this command build patched OSS fuzz, and we need to just navigate into the OSS fuzz integration directory as follows. And now we can run the build patched OSS fuzz. And that's exactly what we're going to do now. So what will happen now is that it will clone OSS fuzz, it will apply a few patches, and then it's going to build the Docker images of OSS fuzz. Although it will have a few changes in the Docker images, but that should soon, and that's exactly why we have to rebuild these Docker images rather than say just pull the recently built ones off them. Now this is going to take a while because it will have to build a modified version of Clang, and yeah, so I will just wait. It will probably take an hour or so, and once that is done, then I will return this video. Okay, so the Docker images are now built, and we now have an OSS fuzz folder that we can navigate into, and we have the all of the files that are relevant for OSS fuzz here. So this is the OSS fuzz repository, and we can also see that there are a few changes made to various files in OSS fuzz, and these correspond to the changes that we have in Fuzz Introspector at the moment. Now, what we're simply going to do is we're going to follow these instructions, which says use this run both script, and this will be the name of the project that we're going to analyze, and this will be the number of seconds that we are going to run the fuzzes. So we're going to run these fuzzes in order to collect some runtime coverage that will be used in the analysis report, the Fuzz Introspector analysis report. So I'm going to run that script, run both, and then htslib. And I'm just going to give it, let's say 800 seconds to get a little bit more substance in terms of having the fuzzes run for a bit more time. So that's running now, and this will also take a while. So this will actually run the fuzzes, first build the fuzzes of the htslib project, and then it's going to run each of the fuzzes in the project for 800 seconds. After that, it's going to collect the code coverage, and then it's going to do a Fuzz Introspector analysis, and then it's going to merge all of the data from all of these runs into one report where you can read about it. So I will just pause the video again and then resume once the report is up. Okay, so the analysis is now finished, and you can see that it simply tells us that we can go to our local host on port 8008 where the report will be. So let's just navigate there as follows. And then we're also going to simply click on the fuzz report.html, which has the Fuzz Introspector report. Make it a little bit bigger. And it will take a while to load just because there's a lot of data inside of it. And when you have large projects, that can be a little bit of a block at the moment, but we already finished loading now. So let's just zoom in a little bit. And this is the dashboard presented by Fuzz Introspector. So let's just see here what the report tells us. So first and foremost, it shows an overview of the reachability of all the fuzzers in the project relative to how much of the target project that they cover. So it tells you about how much of the cyclomatic complexity in the target project is covered by the fuzzers, so reached, and also how many of the functions are reached by the fuzzers in the project. And this is all static information, so it's data that is based on extracting the control flow graphs from the fuzzers in the given project. And we can then also see another table here that has an overview of all the fuzzers in the given project. And in this case, we only actually have a single fuzzer, and we can see that this fuzzer reaches just around 1,000 functions, which corresponds to, we can see up here, half of all of the functions in the target project, and just about 60% of the reachability, of the complexity. And we can see various metrics about the fuzzer, such as the maximum call depth is 17, and the number of files it can reach is 67, and the total accumulated cyclomatic complexity, and so on. So these two top tables here are just a way to get a quick overview of the project. The real interesting table is this project functions table, and this table lists each of the functions in the target project and then various attributes of each function. And this includes stuff such as what's the call depth of this function. It also tells you how many fuzzers reach this function. It tells you the instruction count, which is the sort of LLVM IR instructions, the basic block count, the cyclomatic complexity of the function, the number of functions it reaches the given function, and also the number of functions that reach this function. And then it also has an accumulated cyclomatic complexity, which is the cyclomatic complexity of all the functions reached by the given function. And then it also has the undiscovered complexity, which means that this is the cyclomatic complexity that is not covered by any of the fuzzers. So and this table is fully sortable. So we can, for example, try and identify what's the function with the largest accumulated cyclomatic complexity. And in this case, it's LLVM fuzzer test 1 input, which means that it's actually our fuzzer that has the largest that is the most complex function in terms of that reaches most of the code. But now we can also very quickly see that there is that the undiscovered complexity is 3 if we hit that function. So I think there's a little bit of an issue here in that it should actually be 0. So we can see that if we create a new fuzzer that target in fuzzer test 1 input, which of course we shouldn't, it should actually be 0 here. So there's a little bit of a bug here, but we can then see what is the gain we get by looking at the undiscovered complexity. What's the gain we get from analyzing that function? And we can see a full list of all of the accumulated complexity, and we can try to sort which is the function that has the largest amount of undiscovered complexity for us to target. And that would be vhopen libcurl and a bunch of other functions. And notably, we can see that only a subset of the accumulated complexity of the given function is actually undiscovered. And that's because this given function will also call into other functions that are actually covered by the single fuzzer that exists in this case. So these metrics here, we use them a lot in terms of quickly identifying interesting targets. So if you were to generate a new fuzzer for this target, you would, for this whole project, you would kind of identify what are the functions here that have the largest undiscovered complexity, and then you would create, say, a fuzz driver that would target the S3 open, or at least involve the S3 open function, and so on. So this table here is really useful when you have a project and you want to quickly understand what are the most complex functions in the project. And we can see here the actual functions with the most accumulated cyclomatic complexity. They are all reached. So we can see that it has the fuzzer hit count. It has 1, 1, and then we have 0, just because we don't count this one. Fuzzer as one input. That should probably also be fixed. But then we can see that there are actually a couple of functions here which are not hit by a single function, by a fuzzer. And they have quite large accumulated complexity, but they only have very little undiscovered complexity. So this is probably because these index build functions, various sorts, are simply just wrapper functions, and they are most likely just wrapper functions of one of the functions that are also in this table that are shown right here at this page in the table. They are most likely just wrapping, say, view VCF or so. Well, not view VCF, because it has to have a small accumulated complexity. So one of the lower functions down here, which is not hit by the given fuzzer. So this is a way to so this table here, project functional view, is a way to very quickly get a sort of be able to direct you towards what you should look for when writing, if you were to write a new fuzzer. Okay, so let's go down a bit further and we will see a section which is called fuzzer details. And in this case, we will have this call tree down here, which shows the entire call tree of the fuzzer with coloring based on whether in the coverage execution, whether this function or this call site was actually hit. So we can see that the LLM fuzzer test1 input function was hit in the coverage execution, which makes sense. But we can start to see that there are various functions that have not been hit. And these include these are all of the sort of like points in the coverage analysis that was not hit. So we can follow the link here, which gives us the exact location in the coverage report that shows where this call site to abort actually happens. So if we just open this tab, we can see that there's the call here to abort, and that abort only happens when malloc returns null. So it makes sense that this piece of the code is not actually executed. Now we can use this to very quickly understand what parts of the target project is being hit, and we can very quickly identify locations that need some type of analysis. So for example, we can see here this call site is hit, but the free just above it is not hit, and we can try to inspect and verify that it's actually true. And indeed, we have the free right here, which is being hit, but the free right up here is not being hit, and this is just a reflection of the call tree here. Now, the interesting bit here is we want to very quickly identify where is there a transition where the fuzzer should reach a certain piece of code, but we actually don't reach it. And we can do this using this table, which shows us the largest places where it goes from green and yellow to red. So where there is the largest occurrence of red, meaning unhit pieces of code in the code tree. And we can sort that by block nodes, and we get this location right here, which happens to be call tree index 2104. That corresponds to this call tree index you see here. So we can simply search for 2104 now, and we will see a location where it goes from being green to a lot of red stuff. So this is the location where in the coverage analysis, it will never execute any of this code. And this code is the largest place where there's the largest collection of uncovered code. So we can just look at the call site where we actually call the SAM header right, which is right here. So we do call into the function, which we show it's green, but we actually never, but we exited, it looks like, instantly in the function. So let's look at the actual function itself. And we can see that, well, it executes here, but then we can see that there is a bunch of code in the beginning that is not executed, although we do execute some code further down here. And we can actually see that, so this shows the call depth relative to the entry point of the fuzzer. And if we scroll a little bit down, we should be able to see 3 at some point that is green. And that shows that should show the code that we have right here. So let's just go further down. And that's right here. And this should be just at the beginning of the, so that's this function right here, which corresponds to just the entry point of the SAM header right function. So, which is this one, which should be this function right here. Okay, so the main point is that this piece of code, which is uncovered at the moment, is actually not hit during the coverage analysis. And if we could trigger this code execution, we could make the fuzzer potentially execute all of this red code here that you see. So we will now try to do a little bit of analysis in terms of why we don't reach that code. And the way I would go about this is I would look at the specific location where this call happens, which is look at the call site itself. And then I would just see that, okay, so this happens within the view SAM function. And we can see that the parameters or the arguments passed to it is header, which is simply, which is assigned here. And the header depends on the int variable, which is an argument to view SAM. And then we also have the first argument to SAM header right, which is out. And that argument is essentially independent of in, it seems, since it's just assigned to the return value of SAM open, which has a fixed, which has constant arguments. Now, if we look at the SAM header right function itself, then we will see these functions are only triggered if the fp arrow format.format is equal to certain types here or certain values. And fp here corresponds to the first argument to SAM header right, which means that the first argument needs to have a certain field set in it, so in order to trigger these variables. In order to trigger these code parts. So what we saw before was that the first argument to SAM header right is actually a fixed value, it seems. I haven't analyzed this in depth. That is assigned the same thing in each run, because these arguments do not depend on the value of, say, which is input to the function. So now we essentially need to understand SAM open, and whether SAM open will always construct a SAM file pointer that has a fixed set of values in its format.format. And most likely it does, or we need to just trigger some conditions within SAM open in one way or the other. But this is where further root cause analysis would be. But the point is that we are very quickly isolated that what we need to do is we need to analyze SAM open here in order to identify how we can force SAM to return a pointer that has format.format equal either binary format, BAM, or CRAM. And if we can do that, then we will start to trigger this code, which will make the fuzzer execute a lot more code. So that's essentially the point here. Another point may be that we should actually integrate a new fuzzer, because SAM header right must be called in a different way than this piece of code does, because this piece of code will have a fixed output here, it seems. And thus it may be that we should implement a fuzzer that has this code pattern in itself, but has some type of variable, also fuzzer inspired arguments passed to it, such that the return value can be of all sorts. So that's essentially how you can use this whole call tree analysis, which overlays the statically extracted control flow graph and dynamically extracted coverage information, how you can use that to understand how the fuzzer is performing. And there's some other graphics in here which tries to make the tries to make the understanding of how the fuzzer performs easier. And this is a visualization of the call tree of the fuzzer with coloring of all the nodes in the call tree and how they were observed during the coverage analysis. So this is the fuzzer details section, which we can see out here. And then we also have a section that is called analyses and suggestions. And this is essentially a section in the Fuzz Introspector report that gives suggestions as to what you should do in order to improve the fuzzing harness for the HTS lib project. And here we have a table that shows all of the optimal interesting functions that you should target, which means that if you implement fuzzers that will also reach these functions, then you will have just about 70% of the complexity achieved, whereas before we was just about at 60%. And this is kind of like an optimal function analysis, optimal function target analysis. So it tries to identify what is the smallest set of function that will reach the largest amount of new code to hit. We also have a little bit of very simple synthesis for fuzzers, but this is very exploratory at the moment. And then we have another functions, a table that shows all the functions in the project and all of the all of these coverage data and matrix data, all the various attributes of each function, assuming that these targets will also be hit. So the analyses and suggestions section will give you a lot of information, such as guides as to you should implement fuzzers that will target these functions and that will improve your fuzzing harness, which is described in terms of here, how much gain you will receive. But this tree is really one of the key ideas in terms of we want to have a quick overlay of statically extracted control flow graph and call tree with the coverage information. And we then have a few heuristics here in terms of identifying quickly what are the spots where your fuzzer should actually proceed and uncover more code, but it doesn't. And so that's it for this short introduction to Fuzz Introspector. It's still being developed a lot, and it is also being integrated into OSS Fuzz itself right now, not just through the Fuzz Introspector side. So this will soon also be available to a lot more projects on an automated basis. And obviously we welcome any contributions to the project in GitHub, and we would love to see ideas. If you have ideas for what would be a nice introspection information about a fuzzing harness and a project, we'd love to have ideas, and you can just put them in the issues or submit a pull request or something like that. But that's it for the Fuzz Introspector introduction. I hope you enjoyed it. Thank you.